the concept of 3D trusses is based on the same ideas that you looked at under two-dimensional truss systems. So if you look at this question, for example, the only difference here is that now we're looking at a third dimension. So you have the y-axis this side, and then we have the z-axis projected to be the vertical one, and then we have the horizontal axis, the x-axis, which is labeled to be this. So here, where they've put y here becomes the positive direction, and then where we have this one, this becomes the positive one. Then we have z being positive going upwards. So yeah, the same rules for vectors for these coordinate systems will work. If you guys observe how this course has been proceeding, it's been building on from what you guys started. We started first by looking at how to find components. Then you went on to looking at how to express forces in Cartesian vector form. After that, we moved on to how to get dot products if you wanted to get a component in a specific axis. After the dot product, you also moved on to look at the cross product when evaluating a moment. So all those are going to be helpful here. And you know to say, when adding components, if you can express forces in Cartesian vector form, then adding them becomes easy because everything that has unit vector I means it's an X component, add them together. Everything with unit vector J, add them together, they are Y components, and so on. So 3D trusses are actually based on that. And the approach that we're going to take to working out these questions is going to be more like an extension of the method of joins. So we'll be approaching one joint after the other. We'll look at joint A. You can also look at joint B there. So the question is basic. Determine the forces acting in the members of the space truss shown in the figure. Indicate whether the members are in tension or compression. So this is what they are asking us to determine. Now, how do we do it? Well, just like before, you want to find where you have a lot of known forces and less unknowns. So if you compare, you have two dominant joints here. So you have this joint here, the joint at B, and you have the joint at A. So if you look at the joint at A here, you quickly notice that at A, we have one given force, the force P, but the unknowns we have 1, 2, 3 unknowns. But if you compare it with joint B, for joint B, what do we see? We have one known force, that 2 kilonewton. But how many unknowns? 1, 2, 3, 4 unknowns. So clearly between the two, will favor joint A. So let's start with joint A. Now, how do we approach it? Well, the first thing that you have to do when it comes to 3D trusses, you want to express all the forces in Cartesian vector form. So, well, just like in the method of joints when dealing with 2D trusses, you want to pick a direction for the forces in each member. So you can create a sketch, but in 3D, I think a sketch is a little bit very hard to picture. So instead, I'll just pick the joint A there. So that is my joint at A. Now what I'm going to do from there is I'm going to assume direction in all the members. So we have, this is the given force first. So that is the force P. So this is the force P. Now, after we have the force P labeled, now I want to indicate the forces in each of these members. So I have AB here, I have AE here, then I have AC down here. So I want to label them. So how do I label them? Of course, using the method of joins, you want to assume direction. So I'm going to assume, just like how I have been doing in all the other cases, I'm going to assume all the forces are going away from the joint. So I'm going to assume the one along the member AB is running from A to B. So I'm going to assume this is something like this. So I'll say this is F, AB. Then next up, I have one going vertically downwards from A to C. So I'll say that is F, AC. And lastly, the third one from A to E. So I'll show this one to be something like this. And this will be F, that's AE. Okay, now just to help you guys remember how this goes, let's say you have this is the member, and this member is, I want to show this one from A to B. So this is AB. Picking a force at this joint to be a force like this one. What does that tell us about the force, the state of the member? Is the member in compression or in tension? What do you guys think? Do you remember how it goes here? Then it implies that the member is in tension. So all those are still going to play a role here. But let's proceed. So I have shown all my forces acting at the joint A here. Now, the first thing that you want, after doing this, of course, what you want to do now is to express each of these forces in Cartesian vector form. Now, how do you do that? Come back to your diagram. So when you look at them here, they look all weird. But remember, this is 3D. The easiest one perhaps to sketch here is the force P. So how would you express the force P in Cartesian vector form? So let me ask you guys to try that. Can you guys tell me what the force P is in Cartesian vector form? Look at it very well.
Negative J?
Negative 4J. So yes, it is in the negative J axis and it comes out as negative 4J. So if you're going to show the units there, this is kilonewtons. So the force P has been dealt with. Well, the easiest one here, the next one that you can see here, is the one along the member FAB. So that one should be easy. I hope when you look at it, you should be able to see it as well. So the force along the member AB, so I'll present it in terms of the magnitude multiplying the unit vector. So for the magnitude, since I have no clue what it is, I'll take the magnitude as just FAB. So notice that when I'm writing the magnitude only, I do not have that arrowhead on top. So this is just for magnitude without direction. Now to give direction, I must specify the unit vector. But for this one, it's a little bit easy. So what is the unit vector in the direction of the member AB? So what is the unit vector there? Yeah, this one comes as positive J. Okay, so that one is sorted as well. Next, we go to AC. So let's look at FAC. So again, I have no clue what it is, so I'll present it as the unit, the force, not force vector, the magnitude of the force AC, multiplying the unit vector. Again, look at AC. Where is AC? AC is this one here. What is the unit vector pointing in the direction of AC? Z-axis. Be specific now. Is it up or down? That's negative Z, right? So because you see, my assumption is that it is pointing downwards. So because of that, I'll bring a negative here and I'll put the K to mean it's in the negative K direction. So that sorts out two of my forces, but I still have one. See, for the fourth one, the one remaining FAE. So for this one now, I have to do a little bit of work. So I will, pardon, we've got a question? Go ahead.
The position of
AB. Finding the position vector.
I can go back to the diagram so that explain the question. Let's take a look for a derive and the indicator. What is going to go in the very first
You mean going like from here, going like this?
yeah, something like that.
Then like this. Is this what you mean? Okay, who can answer this for her?
Is it because we're looking at the joint A?
Exactly. So we're not starting from C. Everything is happening at the joint C. So observe where my point is. So we're looking at the joint C, A, I mean. So we're starting from here. So notice that from A, we don't go up or down to reach point B. We only move from that point along the y-axis. We only come up to that point. So this is along the J axis. See that the two axes are parallel to each other. Have we answered that? No, great. Do we have any other questions before we proceed? Okay, so this is where we actually have a little bit of work. FAE. For AE now, this is where you really need to know what is happening, because you're going to express FAE as the magnitude, which is FAE. We don't know what it is, so just put a label, FAE. But it has to multiply a unit vector in the direction of that force. You see, in all the other three cases, the unit vector was just something specific. It was negative J, positive J, negative K. It was just one thing. It was easy. But in this case, the unit vector, now we have to do a little bit of work in terms of finding the unit vector. So let's find the unit vector that runs in the direction of that force. That is from A to E. How do we get that unit vector? So we need a displacement vector from A to E divided by the magnitude of that displacement vector. So can we find the displacement vector running from A to E? Who can give us the displacement vector? Look at the description here. So I want the displacement vector from A to E. What will be the displacement vector there? Yes, Joey. Cheryl, go ahead. Cheryl, you have your hand up.
Sorry, I was saying it will be positive 2i, positive negative 2j, and negative 2.
So positive 2i, that's from here to there in the, so like that. From okay, so that's from here to here in the x-axis, positive 2i. Then you have negative 2j, so that's negative 2j. Positive. So remember, Chewe, when starting, I said because they've put their y here, they are telling us that the y-axis is positive in this direction. The z-axis is positive in this direction, and the x-axis is positive in this direction. So just be careful there. So this is positive 2j. And the last one is in the z-axis. In the z-axis, you had to go down from A. Remember again, I'm coming from A going to E. That's the direction of this vector. It's from A to E. I go down, then positive X, then positive Y. So positive, in the z-axis, it's minus, that's 2 again. Let's get its magnitude. So that's literally just the square root of 4 plus 4 plus 4, as in 2 squared plus 2 squared plus negative 2 squared. So which is just root 12. You guys can correct me if I've made an error anywhere. So get the displacement vector, which is 2i plus 2j minus 2k, but then this is going to be divided by root 12. We can actually get the answer or what this is in decimals. Or we can leave it like that, but let's get it in decimals. So we see that our force FAE, this becomes equal to, so FAE, the magnitude of the force, multiplying the unit vector. So for the unit vector now, I want you now to divide, let's just keep it. Just keep it. 2 over root 12 I plus 2 over root 12 j minus 2 over root 12 k. So this becomes the force FAE. Now, if you are able to do this up to this point, then you are almost set, because the next part is perhaps the easy part. So let me just distribute that FAE. So I have 2 over root this FAE I plus 2 and finally this is minus. Okay. So now the next part is to use the equilibrium conditions. So you were able to get the forces, express them in Cartesian vector form. The next part is now to just apply the conditions of equilibrium. And the best part here is all we need is the first condition of equilibrium, nothing more, nothing less. So let's see how it goes. So from the first condition of equilibrium, what we know is that the sum of the forces must be equals to 0. So when we add the forces in their respective axes, we should get a 0. So for our joint there, let's try to add the forces. So let's start with the forces in the x-axis. Let's sum forces in the x and equate to 0. So let's see, which of these forces have an x component? So we start with this one. Does this force have an x component? So let's start with this one. Do we have an x component there? So for the first one, we see that we don't have an x component, so we bypass it. For the second one, we see that we don't have an x component again, so we bypass it. For the third one, again, that's k, so that's not an x component, we bypass it. And then for the fourth force, do we have an x component? Yes, we do. I represents the x component. So we have 2 over root 12 FAE, the only x component present. So because it's the only one, so it becomes this has to be equals to 0, implying that FAE has to be equals to 0. One of the forces has been determined. FAE must be 0. If you think about it, 3D trusses are actually even easier than 2D, because in 2D, because they know to say they are easy to see and so on, it's easy to complicate them. But for 3D trusses, most questions that will be brought in your exam, there'll be questions like this same one where it's very basic, just sum of forces and you're getting answers. Okay, so that first one has turned out to be 0. Let's sum forces in the y-axis and also equate to 0. So again, want to go back, identify all the forces which have y component. This one does have a y component, -4. So we have -4 there. What else? The next one, let's go to the next one. We have this one. Yes, this also has a y component. So this is going to be FAB. So FAB is in the y-axis, so we have plus FAB. Let's go to the third force. Does it have a y component? So the third force is this one. It's in the k-axis, so it doesn't have a j component or a y component, so we skip it. We go to the last one, and the last one does have a y component. It's positive 2 over root 12 j. So I'll just copy this one. So that was the last one. So we just equate this to 0. So in the end, we see that FAB plus 2 over root 12 FAE is equals to 4. So let's hold on to this for now. So let's now.
But sir,
yeah.
haven't we found FA to be 0? So
Ah.
when that just remains.
Nice. We already have what FAE is. So because we have it, just plug it there. So because we know what FAE is, this reduces to just FAB being equals to 4 kilonewtons. So we have now found what FAB is. And having found this, what is its state? What can we conclude here? Is it in tension or compression? Remember my assumption? Yeah, my assumption was that everything was in tension. So if it comes out positive, then it is in tension. So this is tension. So we then move on to the third axis, sum of forces in the Z. But before we start this one, do we have any questions on the previous one or what we've done so far? Okay. Looks like we're okay. Let's see how it goes. So the next part now, I want to sum everything in Z. Again, when you look at them, okay, someone trying to join us. Okay, done. Okay, so we start again. So with the first one there, you see it is all in the y-axis, no z component here, but we see that FAC has a z component. So that's minus FAC. So sum of forces in the z, we have minus FAC. What else? That was the third one. So we go to the fourth one. So this is what we've written there. So we go to the FAC here. So we go to the fourth one. The fourth one is this one here. So we see that it also has a z component. So let's just copy that z component and add it there. It's negative, so we get it with its minus there. So only 2 of our forces actually have z components. So these 2 must add up to 0. But remember again, we know what FAE is. So because FAE is known to be 0, this makes our work even easy. So this means that we have FAC equals to 0, or yeah, just FAC is also equals to 0. So from summing forces about point A, we have found 3 things. Let me highlight them. So what we have found is that 1, FAE is equals to 0. 2, the other one was what? FAC is also equals to 0. Then we also found AB. FAB is equals to 4 kilonewtons. And it is in tension. So we have found 3 forces, or we've sorted out 3 members. Now we need to do more. So the members we have sorted out are members which are, let me just show you. These are members which are here. So this sorts out this one, and this one. So we still have this one here, and this one here. So to sort out those 3, we now move on to look at the joint at B. So let's go and look at what is happening at that joint. So moving on to joint at B here. Are we okay with joint A? Any reactions from that? So again, for the joint at B, what I'll start with is you want to draw a free body diagram. You want to, but again, figuring out how you're going to draw a free body diagram on a piece of paper might seem to be very, very hard. So instead, I'll just draw the point, say this is my joint B. Now what I'll do is I'll just show the forces, how they interact with that joint. So this is the applied force, and it seems to be acting vertically downwards. So that is the 2 kilonewton force. Now I want to indicate the other 3 forces, and these are the forces in the members. So I have AB, and remember I already found the force FAB, and according to our calculations in the previous case, FAB turned out to be 4 kilonewtons. Now, where was it pointing? Was it pointing toward the joint or away from the joint? Do you remember? Nice, away from the joint. So remember at A, it was pointing away, meaning at B, it will also point away. So for FAB, it's already known, so I don't have to make an assumption. I'll use what is known. So it is pointing away from the joint. But for the other 3, because they are not known, I will use assumptions again. And as always, for simplicity, I'll stick to the assumption that I've been making. Assume that they are all in tension. So I'll assume this is going like this. I'll assume this is also going down. Clearly, it has to go up, but I'll pick it that it is going down. And I'll say this one is also going like that. So I'll label them. This is F, BE, this is F, BD, and this is F, BC. And of course, this is F, BA. When you do this for some time, you should see why assuming this to point up is the wiser choice. And assuming that, which one is that? Assuming that perhaps one of these, this and this, one of them has to point the other direction, is actually a wiser choice there as well. But for simplicity, you can always pick anything and it just adds up to. So I've picked anything, even though I know it's not the case. I've just picked them to be like that. Okay, so we have indicated all our forces, and just like before, we want to show these forces in Cartesian vector form. So I'll just get this. Let's show all these forces in Cartesian vector form. So let's start with what we already know. Let's assign this force here. We can assign it any character, really. Let's just say this is, we already had P in the previous case. Did we? Yeah, it was P. Let's say this is, let's say B. So let's say the force B, we know that by looking at it, that is coming out to be -2, and it's going downwards, so we're going to say -2K. And we have kilonewtons. Next up, let's move on to FAB. I wrote BA, that's okay. Again, this one is known. So it's, can you guys tell me the direction? What would be the magnitude is 4? What is the direction there? Negative what? Unit vector. No. Yeah, it is in tension, but I'm writing them in Cartesian vector form.
Negative 4J.
Yes, negative 4J. Okay, next up, let's look at the others. Well, FBD seems to be the easiest one to account for because FBD is just going straight downwards. So because of that, we can easily assign it something there. So we have BD, and that is coming out as FBD. And since it is going down, we'll give it a minus there, and it is in the vertical axis, so it's in the K direction. Okay, so that sorts out everything else except these two. So we now want to sort out those two, and how can we deal with them? So for these two, you notice that they actually have components. It's not just in one axis. So our work starts just at the beginning. But let me just express them in the form FBC is equals to FBC itself, then multiplying a unit vector that runs from B to C. Same thing, FBE is equals to the magnitude multiplying a unit vector from B to E. Now it's these that we have to find, the unit vectors. So how do we find them? So let's start with FBC. How do we deal with FBC? Well, let's come to our diagram. FBC. So I want a unit vector that runs from B to C. So the unit vector we need the displacement vector from B to C divided by its magnitude. Okay, so let's find RBC. So to move from B, remember again, from B to C, because I picked my direction to run in this way. So because of that, I need to start from B first, come to A. How far do I have to move? That looks like a 2. So that's 2. But that is in the minus y-axis. So this becomes minus 2j. And then from there, we go downwards and would have reached C. So that's downwards, so that is minus 2k. So this has to be divided by the magnitude of this. So the magnitude of this, notice that this one doesn't have an x-axis, so it only has this. So the magnitude, it's going to be just negative 2 squared plus negative 2 squared, which is root 8. So this is what we get. So that in the end, for this one, UBC would just be minus 2 over root 8 j, then minus 2 over root 8 k. Any questions there? So this sorts out the first one here, that's the UBC. So where there's UBC, I can just put that unit vector that we have found. So we get this one. We can actually simplify it or distribute that FBC inside so that we get FBC is now just equals to minus 2 over root 8 FBC j minus 2 again over root 8, and then you have FBC k. Now we move on to the last one. Let's now find UBE, the unit vector in the direction BE. In the same way, unit vector from B to E. How do we do that? Again, from B to E, that's from B to E in that way. So observe that in this case, you have to go vertically downwards to D, and then from D, parallel to the x-axis to reach E. So this one doesn't have a y component. So in the x-axis, we go along the positive x-axis, So that is going to be plus 2I. Then in the z-axis, we're going downwards, so that's minus 2K. Then again, the magnitude, just the square root of those, which is just going to be the square root of 8. So that becomes the unit vector. So in the same way, we take it the other side. Let me just distribute it. So this is 2 root 8 I minus 2 root 8 K. So we're done with this as well. It becomes FBE multiplying the unit vector. So we have 2 over root 8 FBE minus 2 root 8 FBE. Okay, so this becomes FBE. Okay, now all our forces have been expressed in Cartesian vector form. So the only thing left now is to sum the forces. So any questions up to here? Okay, looks like we're okay. So let's now sum our forces. So where do we start from? So the first part, let's sum in the x. So we're summing forces in the x at joint B and equating to 0. This is again the condition of equilibrium. So in the x-axis, which of our forces have x components? For this one, we saw to say we have how many forces? We have 4 forces. Is it 4? 1, 2, 3, 4, 5. If we count that applied 2 kilonewton force. So I have 5 forces. So we start with the force P, not P, sorry, it's not that one. It's, where is it? The force B, the point joint B, yeah, here. So these are all my forces. So let's start with the force labeled B here. This is in the K direction. It doesn't have an X component, so we skip it. This doesn't have an X component, we skip it. This one does it have? This one doesn't have an X component as well, so I skip it. This one doesn't have as well. I wrote it here in full. It doesn't have an X component, only has J and K. X component means I should see I there. So I skip that one as well. So looks like only one of these forces actually has an I, which is this one. So this one has an X component, and the X component will be this part here. So for this one, we're only going to have 2 over root 8 FBE as the only X component, so it becomes the only thing equals to 0. And again, you see that FBE becomes equals to 0 straight out from the beginning. So let me hold on to it, FBE. So I had the other 3 taken note of. So let me add it to this set. So this is what we have. And to this, we've just found FBE is equals to 0. Let's proceed. So from
Sorry,
some...
how is FB equal to 0 when it has 2 over root 8 there?
Okay, so the idea here is this. If you have 2 over root 8, multiplying FBE and saying the answer is 0. So you're multiplying a number with an unknown. So, you know, when you get it, huh?
Yeah.
So it's only logical that this is the one that is 0. Okay, so let's proceed. So now we sum forces in the y-axis and say this is equals to 0. Again, same condition of equilibrium. So let's go back to our questions again. Let's check our forces, I mean. Which ones have y components this time? So that's here. So we start with the force B. It doesn't have a y component, so we skip it. And guess what? This one has a y component, which is minus 4j, minus 4. So we have minus 4 as the first y component. Let's check what else is there. So again, B doesn't have, this we already got. This one is not a y component because this is a k. So that one doesn't have a y component. So look at this one, FBC. FBC has a y component, and it's this one here that has j there. So we copy the y component. So that's the y component there, so add it to this. So FBC has a y component. What else? So I've taken note of FBC and its y component. The only force that is left is FBE. Does it have a y component? It doesn't have. It only has an x and a z component. So it looks like I only have two y components. So these two must be equals to 0. So from here, we see that minus 2 over root 8 FBC has to be equals to 4. So that, of course, we end up with FBC has to be equals to minus, this becomes 2 times root 8. Okay, so we're seeing 2 times root 8 here, and it's minus. So what will this give us if you simplify this? Try to use a cash. Negative 5.66. Okay, so how do we conclude then? We know to say we don't want that negative there. So how do we conclude, also specifying the state of the member? FBC is equals to what?
6 kilonewtons compression.
5.66 kilonewtons, and this is in compression. So again, the assumption is that all the members are in tension. So when we find a negative like this one, it means that it has to be compression. Okay, let's include it with what we have found. That's FBC, 5.66 compression or kilonewtons. Okay, that one has been sorted out. Now we sum in the Z. Sum of forces in the Z-axis is equals to 0. So same thing. Which of our forces have Z components? Well, now we see that the applied forces in the Z, minus 2. So that's minus 2 there. What else? This is in the J, doesn't have a Z component. Well, this has a Z component, minus FBD. What else? So if we continue, minus FBD noted. Well, FBC also has a Z component. So just copy the Z component from here. So that's done. Now check the last force there. Does it have a Z component? That's FBE now. FBE also has a Z component, so I'll just copy this one too. So that was the last Z component. So with this as the last one, so I'll say equals to 0. So this is what we have. That's a lot. But let's see, do we know some of these forces? So let's see. FBC. FBC, we know what FBC is, so we know what this one is. What else do we know? FBE. FBE is 0. We know what this one is. So you see that this has gone to become 0 because FBE is 0. So our expression becomes minus 2 minus FBD minus 2 over root 8. Where we have FBC, we put that 5.66 6, 6. But I have a question here. I have a question for you guys. How are you going to assign the symbol here? Will you put the positive one, which is the answer we stated, or will you put a minus here, which is the answer you found?
A minus.
Okay. So we put the answer that we found. Remember, this is what we have been working with all along, that it has a minus here. So we must carry that. It's only when presenting it that we actually show the correct symbol there. If you wanted to use the positive one here, it changes everything. The diagram that we drew earlier must also be changed so that directions must be respected. So we stick with what we started with. The minus has to be included. So this becomes equals to 0, since this term is 0 here. So the 2 goes the other side. We now have or let me take the minus FBD the other side. Remain with minus 2. Then this becomes plus. Can you evaluate this? What will be the answer here?
(6.00 kilonewtons) negative.
Negative. Is it negative?
I was giving the sign. I was giving the final answer. That was negative. That was minus. Oh, that was 4.00.
Oh, this is, yeah, it's not negative. It's not 6 then. This is 4.00. And you see, there's this minus here and there's this minus here. They'll make positive here. Have you seen that?
Yeah, just send that.
Okay. So that the final answer then for FBD becomes equal to 2 kilonewtons. And because it has turned out to be positive, then our assumption that it was in tension stands. So again, let me just copy these. So this is what we have. So we have now found the last one. So that was F, it was BD. And we have found it to be 2 kilonewtons. And it was in tension. Okay, so basically this is how we approach 3D trusses. Yeah, any questions on this? Okay, now what I'll do is we'll end this class here, but I'll ask you guys to now look at these ones. You can say start with this one. Try to see if you can apply the same concepts to this question. Start with the joint at C. See how much you can do. See if you can find what is happening in this member, and that member there. So see if you can work it out for this one. So we're going to do this one tomorrow night. So let's end here. Any questions before we say good night?